thank you all for coming tonight to Team MagNET's Junior Colloquia presentation. My name is Robin McFaul, and presenting with me tonight is Patrick Wu, Noah Wachowski, Sean Wazowski, and Jose Ramos. In our presentation tonight, we will cover several topics. We will start with our goals and background information, go over our methodology, then transition to the project's composition, and our team's current progress. We will then finish with the challenges we've faced, challenges we expect to come up, and advice to the future teams in conclusion. Since our project has changed so much since we last presented, we thought it would be beneficial to reintroduce the focus of the team. Team MagNET's current goal is two-part. First, to develop a microcontroller-powered system capable of maintaining stable magnetic levitation, and then second, to use this device to then achieve rotation through overlaid signals and varying magnetic fields. One important thing to note about our project is it is a fairly new field of study, making our background research a little different from most other projects. We focused more on a few fundamental theories rather than decades of well-developed research. Our research started with Earnshaw's theorem, which states that static or not moving magnets cannot levitate because the system is inherently unstable due to the fact that opposite poles of magnets attract. One way to counter this is to impart rotation to a magnet, causing it to stably levitate at a place in the field called Earnshaw's point due to the gyroscopic effects of the spinning motion. In analyzing this information, we as a team realized that a varying magnetic field could also achieve the same goal of stability as rotation if done at a high enough frequency. This is the method that we have decided to go with in order to create our frictionless motor. This technology can actually be seen in its most basic form in something called the Levitron revolution, which is displayed here. The Levitron is a powered electromagnet and ring magnet system that allows a puck to levitate by implementing the varying field concept. Its base is a completely analog circuit that partially does what we want to achieve, but it lacks the necessary control for our project. So we took it apart and analyzed it to help us implement our own design. From this, we hypothesized that a microcontroller-powered, magnetically levitating system will improve the lifespan of motors that can be internalized, such as centrifuges and hard drives. Our methodology, which we will explain in further detail throughout our presentation, is as follows. We started by examining the existing Levitron system, analyzing both the circuit and its magnets. We will then proceed by programming a microprocessor to mimic the Levitron system, then design a base centered around the microcontroller, test our device, make adjustments as needed in order to ensure the stability, and then create an algorithm to achieve rotation. Okay, so to accomplish our goals, we've currently divided up our work into several subcategories, including circuit mapping, magnet mapping, and coding, which Patrick will now talk about.
So in terms of circuit mapping, we broke it down into two parts. First, we mapped the existing circuitry of the Levitron, which Robin talked about earlier. And then once we got that information, we put it into a circuit lab simulation, which is an online circuit simulating tool. So in terms of the physical circuit, we first looked at the circuit and figured out which components there were on the circuit and identified what they do individually and, more importantly, how they work together to achieve levitation. After we got that information, we put it into Circuit Lab in the hopes of deriving an algorithm that would do the same thing as the circuit but with code. So here's a picture of the physical circuit. If you look, these are inductors. In the center of them are Hall probes, which you can't see clearly here, but we'll go into more detail later. Over here are the two op amps, and centered in between them is a switch. And up here we have transistors. So here's a list of the components that we're going to go into detail today. So like I said, we have Hall probes, the integrated components, which include the op amps, switch, and transistors, and then the inductors. So Hall probes. So as you can see, it's a little bit better. The Hall probes are these black boxes located in the center of the inductor, and what they do is they detect magnetic field in the X, Y, and Z direction. And that magnetic field is going to be produced from the object that we wish to levitate. Based on those magnetic field readings, the Hall probes will emit a series of microvoltages, which will then go into the op amps, which are here and here. So these op amps will receive the series of the microvoltages as a signal, and then that signal will eventually interacts with the switch, which is located in between them. The op amps act as or provide the analog circuit logic, and the switch receives a bunch of multiple inputs, and based on what those inputs are, it will output a single output. That output will then travel to the transistors, these are all transistors, and the transistors will receive that signal and amplify a current up to 2 to 3 orders of magnitude, which will then power the inductors that Noah will talk to you guys about.
Thank you, Patrick. So he previously pointed out the copper coils there, which are the inductors. These are actuators, which means that they're the part of the circuit that exercise control over the levitating object. So after the circuit modifies the Hall probe signals, the inductors change the magnetic field above the base, which stabilizes the puck. Important to note is that because the system is constantly changing, stabilization has to be an iterative process, and the magnetic field needs to be updated consistently. So after we analyze the physical circuit, we have put all of our knowledge into the Circuit Lab software, which Patrick previously mentioned. This allows us to do circuit analysis in order to see how the circuit behaves based on different input readings. And this is important, since Circuit Lab only works with a very specific input system. We won't be able to model the changing readings from the Hall probes, other than simply giving different specific inputs to mimic potential input readings. But this will give us a way to determine the voltage and current at each circuit element with the Circuit Lab system. This will guide the process of creating our algorithm as we move into the coding and construction phase. And it's important here to note the general purpose of using the microcontroller. The Circuit Lab simulation helps us to understand the circuit that's been physically built, but since that is set in stone as a physical object, you can't change the way that the circuit behaves. So using a microcontroller will allow us to modify the way that our system behaves and give us increased functionality and be able to not only stabilize but also specifically impart whatever sorts of behavior we want on our levitating object, specifically rotation, but ideally anything that we could function with our system. I'll now pass this off to Sean to discuss magnet mapping.
So, the goal of this part of the project is to create a three-dimensional magnet mapping. The goal of this part of the project is to create a fully three-dimensional magnetic field of both the permanent magnets and the changes that we can make to the inductors. So we believe that this will give us the strength and orientation of the magnetic field, the degree of instability of our levitated system, and the types of perturbations that we can induce with the inductors, and specifically how they will affect the levitating magnet. So we will use three primary methods to analyze the magnetic field. First is an analytical model, then we'll use numerical simulations. Finally, we'll discuss how we have used experimental measurements to determine the magnetic field. So in our research, we have found an analytical model of the system. However, this model is very complicated. But so instead of using it as the end-all be-all for the system, we're going to use it as a guidework to help us guide our analysis of the experimental and numerical measurements. So next we have numerical simulations. So these were done using finite element magnetic modeling. So what this does is we used it to initially estimate the field strength at around levitation heights. So, but using experimental data, we'll try and get a better fit of this field so we can really truly gauge the strength of the field at all points in space. So if we look at this picture generated by the magnetic modeling, we can see this is the false section of the levitating system. We have the permanent magnet false section here and here, and the levitating puck here. These lines are magnetic field lines, while the colors indicate the relative strength of the magnetic field, indicated by this color bar here. So next, we have the actual experimental measurements. So what we did is we used a device in our mentor's lab that can map the magnetic field. So there are 3 fields that we would have currently mapped. The first is the ring magnet's axial field, so that's the field going up and down, and as well as that as the puck. And in addition, we have the puck's radial field, that means the puck's outward field. So this is a picture of the ring magnet's axial field at levitation height. As you can see, it goes up. This provides the magnet that's holding it in place. And then we've got a minimum here, which is where the puck magnet sits as we're levitating. So as the next picture, I'm going to show you another angle of the same picture. So this is the underside, this is the same minimum that we're looking at before, but this is the underside, so we can get a better view. You can see that it's pretty much a parabola here. So next, here's the puck magnet's axial field. This mapping was done right at the surface of the field, and we can see that this is very strong, and this actually provides the bulk of our levitation. So finally, we have the puck magnet's radial field. So the reason why this field is actually really important is that we believe that the Hall approach used the radial field to determine the position of the levitated puck magnet. So specifically, we want to get the decay of the field. So the y-axis graphs the decay of the field along the magnet, while the x-axis graphs the decay of the field, how it moves away from the magnet. So we're interested at the field about 1 inch away from the magnet. And so the things left to map, so the main thing that we're left to map is the perturbations due to the inductors. And we would like to combine the numerical simulations and the analytical model and the experimental data to make a true 3D map of the field. So I'll now hand it off to Jose to finish our presentation.
Thanks, Sean. Now that we talked a little bit about circuit mapping and magnet mapping, I'm going to talk a little bit about coding in general. Now, we've started some preliminary pseudocode, but we stopped actually almost as soon as we started because we realized the bulk of what our algorithms and code is going to look like are going to have clues. The circuit itself is going to have clues to what our code should look like in the future. But we have made some significant progress in coding. For example, we've picked the microcontroller that we want to use. We're going to use a Raspberry Pi versus, say, an Arduino. Now, the reason for this is because the Raspberry Pi has way more input and output ports compared to an Arduino. So that's really going to benefit us because we're going to be using a lot of signal processing. We've also opted for using C as our coding language, as opposed to, say, Python or maybe assembly, because we've settled upon the fact that there's a great balance between the difficulty of coding and execution speed when it comes to C. Python, it would be easier to code, but the execution speed would be lower. And in assembly, it would be impossible to code for us. And C just makes way more sense. Now, this slide is for all the freshmen out there, because we've had a lot of challenges throughout our years. And we think you can learn a lot from this, too. We've had a ton of project adjustments. So much so that we've gone from Team Maglev, a team focused on maglev trains and improving them, to Team MagNET, a team focused on non-mechanical energy transfer and magnetic stabilization. There's also been a huge lack of existing research for our project. Now, what we learned from this was that we have to be adaptable, both in changing our project and in using the basics of research that we have in order to further our project and not be afraid to tread into uncharted territory, because that's really the most fun part of research as a whole. We've also had a ton of trouble with scheduling. You can see there's 13 members. We have 9 majors on our team. It's been impossible, but sometimes you have to make sacrifices for the benefit of the team. Now, we have some other challenges that we're looking for, we're kind of looking forward to in the future. Our algorithm creation is going to take a lot of effort, and we're not really well versed in that, but it's going to be, okay. Well, we'd like to thank Dr. Gomez, our librarian, Nevenka Stravdovska, Dr. Lathrop, Dr. Bowen, Dr. Takeuchi, Dr. Meyergoys, Dr. Cole, Dr. Skendel, the Gemstone staff, and Emma Holmes for all her contributions. Thank you so much.